right? Rest k minus, or we write 2k minus n is the virtual orbital in spin orbital basis. Right? And from there, we know the lowest one that we construct as Hartree-Fock. Right? So this Hartree-Fock determinant or single determinant wave function will be formed from, we're writing here k chi. Let's say start again, get back uh, our spin orbital basis chi 1 1, chi 2 2, chi m. Right? For space orbital, you have to just take two electrons in a space orbital. That's all. That's the difference. We know how to do the spin integration, and we know all the details about this. Right? Now, for exact wave function, will be a linear combination of a complete set of functions, right? Which are orthogonal. I mean, they may not be orthogonal, but it's better to have an orthogonal set. So we have to construct this. Remember that this is having the property of n electrons, right? So each of the member of the linear combination must be also a function of n electrons. So I can write this as some coefficient. Let's say I am writing C I phi, right? Where each phi I is a set of phi I are the n electronic function, right? Out of that, one is Hartree-Fock determinant, right? Which one? The one that gives you the best result, that gives you the about 95% to 99% total energy. Okay? So that's the best one, obtained from the variation principle. So that is one. Rest phi i's we have to construct from this, right? So and then we have to solve this equation. Is psi 0 stand for ground state, equal to E 0 psi 0, right? For all state, I can write as h of psi of I equal to E of I. Right? This is for the ground state, specifically for the ground state. It doesn't matter if you can solve this, we get the exact solution, provided this set is complete. Right? But we know we cannot get that complete for a practical application because completeness means infinity. We can't have infinity, so we have to truncate. So whatever number of basis function we are taking, like whatever number of 2k we are taking, this CI will give you exact result within that basis set. If you enlarge the basis set, results will become better, it will improve, but again, that's exact within that limit. So CI we do, of course, within a limit, is also known as finite calculation limit, but within this limit, this is exact. Now, our question is how to get this psi and how to solve this. So let us first focus on the ground state. How to get this? As we discussed yesterday, the Hartree-Fock, let's say I have this many electrons, spin orbital basis, right? I have three electronic system, I have in spin orbital basis. So these three electrons will constitute my Hartree-Fock. I can construct another member of the set by exciting electrons from here to here, or here to here, or from here to here, and so on. So I get my total psi 0 will be psi of Hartree-Fock plus all possible combinations that we get from an occupied, that we call as ABC or SPU. So all occupied we write as AB, unoccupied we write as P and U. So we get this kind of wave function by exciting one electron from the occupied level to the virtual level. Right? It means that I can take any number of A for any value of A and for any value of B. Right? Basically, what we're doing, we are picking up one electron as if they are filled in the Hartree-Fock determinants and putting them in the virtual orbitals. So if I have total k, this is total is k, or as I said, we have call it 2k, and this is n. Then I can get this as many as 2k n 2. I'm sorry, 2kc2. Those many way I can put two electrons in the virtual orbital, and I also can pick up two electrons by nc2 minus. That is a combination. So if you are asked to take out two electrons from n number of orbitals, you can take from A and B. No, why am I writing two? It should be one. Sorry. I'm taking just one electron, not two electrons. Just one electron from k orbital. So I have 2k minus n c 1. These many ways I can put one electron in this 2k minus n number of orbitals, and I can pick them by this many ways. Right? So this function is not one. This what I mean that this functions is not one. There are n number of functions. There are these many number of functions. So that's about the single electron determinant. And then I can have, when I made a mistake here, this should be R. Then I can have A and B, two electrons from this occupied, and put them any two orbitals in this virtual, but I should not overcount that. So I put this condition A less than B and R less than S. Each will have a coefficient, let us write as CAVRS, phi AV. Right? So these many ways I can have two electronic excitations. And then all possible way I have to do A less than B, A less than B, and less than C, R less than S less than T. So you put C, A, B, C, R, S, T, psi, A, B, C, R, A. This way I can take up to n number of electrons. All electrons I am taking out from the occupied level, and all I am putting them in the virtual level in different combinations. Right? So this is the total wave function. This wave function for psi. Right? And then we have to solve this H psi 0 equal to E0. So, right? That's the thing we have to do. Now, how can we solve that? We solve this by using same linear variation theory by projecting one of the member of this. Like before going to for the solution, let us discuss some of the important things. We have this is the wave function, right? So what about this? So I have wave function. Let us write. Let us call this as psi of Ci, right? And then what is the normalization constant for Ci? Remember that how do you construct the Ci? By taking the excitation from the Hartree-Fock to the virtual orbitals by all possible manner. I constructed this function. So this function ideally should be normalized, right? But let us calculate and see what we get. If we do that, this side will be getting, let's say that let us write as usual. I get psi of Hartree-Fock plus A R C A R I A R, right? Left side also we have similar thing. So I had to pop plus some over of A R C A R psi A R, right? Basically, both side I have done the expansion. I have written them. Is a problem. Let me write it clearly. Over A R psi. Now let us do every part together. This multiplied by that, I get psi Hartree-Fock, psi Hartree-Fock, and then this multiplied by that, what I get? I get C A R C A R psi A R. Let me write the other term. So what I am doing here, the first is this, second one you multiply this by this, what we get? You get here psi Hartree-Fock psi A R C A R, right? Sum over all A and R. For all terms you can do like that. I not write all terms. I write second term as A R C A R psi A R. All possible manner, right? And then somewhere I will get something like A less than B, R less than S. I also have, let me this is write as B and S, C of B S. I'll be writing this as psi of ABRS, psi of CBPU, CABRS, CCBPU. What it means, you don't need to write it completely, but let us understand what does that mean. It means that, you see, this part will come from Hartree-Fock multiplied by Hartree-Fock, right? This will come Hartree-Fock multiplied by any one of the excited, right? So I have just written one term. Similarly, it will be having Hartree-Fock will be overlapping with two-body excited determinant. Hartree-Fock will be overlapping with three-body excited determinant, and so on. If we take this, I get one term which will be conjugate of this. I'll give another term which will be look like this. One side AR, another side let's call it BS, right? To say that they can be different. A can be different than B, so R can be different than S. What I mean that if I have like this, and then you have virtual level, let's say this is R and this is S. So I can have this excitation, one determinant I can get. I can get another determinant from this to this, right? So that is what. Left side I have psi AR, which is single determinant. I can also have sin BS, which is also single excited determinant, right? So all terms will be getting, and this is the same way we get two body excitation overlap with two body excitation. Now look at the importance of this. We can say by inspection that this term is zero. Why this is zero? Because these orbitals are orthogonal. I have a determinant. Let us write a determinant which will be phi of A, chi of A, chi B. Let me write this completely. I get chi of 1, chi 2, and this will have up to chi n, right? The second one, what will have this one? I'll have chi of 1, chi 2. Instead of chi A, which was occupied, I have taken chi A and put in the chi R. Right? Now see, these are normalized. This guy and this guy are orthogonal. So because of their orthogonality, I just get equal to 0. So this term will become equal to 0. Similarly, this all other terms that has cross, right, will be 0. Here also everything else will be 0 except A equal to B or equal to S. Two determinants, when they are same, they are normalized. When they are not same, they are orthogonal. So I get this term survive. This will be surviving only when A equal to B and R equal to S. This will be just AR, C of AR, psi AR, psi AR. Anything else will be just vanishing. Similarly, I get from two body A less than B, R less than S, C psi AB, RS, psi AB, RS. And so on. Right? Now it's the important part. You see, this is according to Hartree-Fock theory, what you consider this is equal to 1. That's what we have started with, right? Hartree-Fock determinant, they are orthogonal, right? So Hartree-Fock to Hartree-Fock is equal to 1. All Hartree-Fock theory developed based on this principle. Hartree-Fock functions is orthogonal. And these functions are also orthogonal. They are not zero. So what I get here, I get sum over AR, a coefficient, square, right? There will be one terms we have missed, square of that. And then from two body, I have A less than B, R less than S, C, A, B, R, S square, right? So what does it tells us? That the CI wave function is not normalized. Is not normalized to unity. It's not normalized to 1. This is equal to 1 plus something. Let me call as data. Right? So many functions that we have derived is not normalized to 1. It's normalized to 1 plus something. But you have to remember that this is a finite term. This is just a number, a constant. Right? So normalization does not need to be equal to 1. It has to be finite. That's the principle. Or to impose a condition psi Hartree-Fock overlapping with the exact function that is Ci, let us call this is equal to 1. Right? what it means. Let us find out what it means. What I'm telling you is sum over of AR, CAR, psi AR plus A less than B or less than S, CABRS, psi ABRS, and all possible excitation up to n body, and then we truncate here. Now what we get here, we get psi Hartree-Fock, which is equal to 1 plus sum over of A normalized to unity, we'll just make the function should be normalized to Hartree-Fock determinant. Now, all we need to do is this. So let us write some of the rules that we already, some of them have spoken in the Hartree-Fock derivation, known as latter rules. Right? This we have done. A function, write this, a function determinant chi1, chi2, and chi-n. If I have an one electronic operator, what is in here? O here, I mean theta here, it is sum over of h of I, right? In this case, if you remember that this was equal to sum over of I, chi I, h, that we have used in Hartree-Fock derivations, right? We have give the argument that whenever these two are equal, this and this are equal, then only it will survive, right? Theta 1 operating on chi 1, I mean h1 operating on chi 1 will survive it is if it is projected with chi 1. Similarly, theta, I mean h2 will be operating on chi 2, give me some other function which will be overlap with chi 2 and so on. And this also have we have learned that chi1, chi2, chi n. This is 1 upon rij or theta 2 part. This was I j greater than I 1 upon rij chi1, chi2, chi n. This was equal to, if you remember correctly, this was equal to half of I j double integration of antisymmetric integration of I j, right? We have done this I comma j I j in the molecular notation I j j I, right? This we have learned. What about if now what is this? This is equal to 34. This is equal to 34. What about I have now, let's say, instead of this, the left part is psi AR and right part is psi 34. What about this? Right? There's a rule. Rule can be obtained by just inspection. It is there in Java. Just read that part if you want. But let me write the rule. This will be just equal to R H. Why it comes? Because this will have A orbital. R is absent. This will, here A will not be there, which is replaced by R. So we will get just only one integral, which is R H A. Right? It means that if determinant of left side and determinant of right side, the bra vector and kth vector are differ at most of one electron, one orbital, then only one turn will be surviving. If they differ, they are exactly same, then n terms will be surviving. If this is the case, if they differ by more than one orbital, then this will be zero. And that also can be understood by inspection. Let us just explain this. What I have here, I have, let's say, I A, I B, let's say H of A, right? And then I1, I, this I will write at R, this I write at S, this is chi A, chi B. Right? Now you see, this can operate on this. Right? So I'll get one term H A chi A, right? In the same, I will have chi J. This will be surviving, but this will be multiplied by chi R, chi B. These two are orthogonal. So this is 0, 0 multiplied by 0 will be 0. So two determinant different by more than one electron will be 0 for the one electron. Similar, by similar inspection, you can also write for the two electronic term. If I have one different AR, sum over of I, sum over of J greater than I, 1 upon Rij, psi RT4. This will give you just one term, sum over of B chi R chi B, anti-symmetrize of chi A chi B. Sum over B, this is as chi R chi B, chi A chi B minus chi R chi B chi B chi B. Right? Instead of two summation, I get just only one summation. The sum will be only over B. And then the third rule for two body, I have ABRS. sum over of I, j greater than I, 1 upon Rij psi heretofore, right? Now this sum will also go, I'll just get this term, chi a, chi, and chi r, chi s, chi a, chi b, minus chi r, chi s, chi. Only one term will survive. This is just like I can write in anti-symmetric form, right? Now if I have more than that, this operator cannot apply it for more than two indices. So if I have the determinant more than two different orbitals, they cannot connect, so we just leave it zero, right? So remember this two. If we have one body operator, then maximum difference can be only one occupancy, singly singly determinant, excited determinant with Hartree-Fock, and I get only one term, right? More than that, it will be zero. For two body operators, I can have a difference. If there is no difference, we get this. If there is difference, if only one, that is singly excited determinant with the Hartree-Fock, I get a n number of terms will be sum over b equal to 1 to n chi r. What is here? A right side, let us, we have a and b, all are occupied. Left side, a is replaced by r, so chi r, and b is as such b. B is not replaced by anything, so all possible b. B can be, this can be b, this can be b, this can be b, and so on. So n number of terms will be survive. If there are difference by two, that is doubly excited determinant with Hartree-Fock, only one term will survive, right? The one that has the difference. If more than two, everything will become zero, right? So that's the rule. As these are called scatter rules. Just remember those. It's not very difficult to remember, right? Now with this, we have to solve our equation. Let us do that. That's very easy. Let us write this. Now what we're doing, we're writing this psi or h of psi ci equal to e of psi ci. Now expand this. This will get me h of psi Hartree-Fock sum over of a r c a r psi a r equal to E is there. If I'm focusing on round state, let us write it round state. If you have E0, and then you write the expansion psi Hartree-Fock plus AR, CAR, psi AR, and so on, right? And then what we're going to do, we're not going to project with psi. Instead, we'll use the intermediate normalization condition. We're going to project with Hartree-Fock, right? And then if I project a Hartree-Fock, first I get this one. And then you write CAR, left side I have Hartree-Fock, then this operator, then we have CAR, and then I have sum over of A greater than B or greater than S, CABRS, I Hartree-Fock is I ABRS, and all other right side will be have same way. We have C0 psi Hartree-Fock. E0 sum over of A R psi Hartree-Fock CAR psi AR. You keep on writing all the terms, right? E greater than B, R greater than S, C A B R S, psi Hartree-Fock C A B S. Right? Now, let us apply our scatter rules. You see, what is this? This is equal to our Hartree-Fock energy, right? That's what I have calculated. I mean, this is E Hartree-Fock. The expectation value of Hartree-Fock determinant with the Hamiltonian. That's what Hartree-Fock energy is. Let us not bother about this term for the time being. We have a simplification for that. CAR A Hartree-Fock is AR. This guy same as A greater than B, R greater than S, C A B R S, psi Hartree-Fock is psi A B R S, and all the term. Let me write one more here, just for our understanding. We'll just write one more. This will be sum over of A greater than B greater than C, R greater than S greater than T, right? C A B C R S T psi Hartree-Fock is psi A B C R S T. Right side you see, because of intermediate normalization and normalization of Hartree-Fock wave function, this is equal to 1. So right side I get E0. Because of intermediate normalization, this term we have imposed equal to 0. That's what the intermediate normalization is. That's what we put the condition. These all are 0, right? Hartree-Fock determinant is orthogonal to all the XLE determinants. So this will be 0, this will be 0. I just get this term. That's all I get. We don't get anything else. Right? Now, what is this? I can now write sum over of A R psi Hartree-Fock is psi A R C A R plus A greater than B or greater than S C A B R S psi Hartree-Fock is psi A B R S. Now see, this term is also 0 according to Saturn rules, right? It is different by, it has Hamiltonian has one body term and two body terms, and the determinants are differ by more than two orbitals, right? So one body term definitely is 0. Two body terms also will be 0 because it differ by more than 2. So, and then it will come as 4 difference of 4. That will be again 0. Everything else will become 0. So I get only this equal to E0 minus E Hartree-Fock. That's all survive. Everything else becomes 0. So my CFF function looks like complicated and lengthy. A lot of functions are there, but we don't need. Everything else becomes 0, right? At least we can uh, have a concept that, or you can imagine that we don't need. But really, it's not true. We need them. This guy right side, if you remember that, that's how we have defined what is called as correlation. Exit energy minus artifact energy is the correlation energy. So I can write this equal to E correlation for the ground state, or let us write E0 correlation. This is just to be called ground state. E0 correlation. This is equal to sum over of AR, CAR, psi Hartree-Fock is psi AR plus A greater than B, R greater than S, B A B R S, psi Hartree-Fock is psi, right? Now we have to find out what is this. This we know, right? How we will find out both of the terms, right? So let us first write this one. Put equation number 1. What is this? Psi of Hartree-Fock. What is H? H was sum over of I, Hi plus I, j greater than I, 1 upon Rij, right? Psi Hartree-Fock, sum over of Hi psi AR plus psi Hartree-Fock sum over of I, sum over of j greater than I, 1 upon Rij psi AR, right? You see, we have just written the Slater rules for this. What is this? This will give me R H A. That's the first Slater rules that we have written. This one, right? What is this? This is the difference between expectation values of two-body operator with the determinants has one occupancy difference, right? Artifact to singlet. So this is, as the Slater rule says, this will over J, not J, yeah, right, over B. This will become RB AB minus RB B. That rule. Rule for the two body terms, the second one, this one. Right? That's all we got from here. What is this? Now, if you remember our expression for the Fock operator, this can be written as R H of plus sum over of B I R star 1 chi B star 2 1 upon R 1 2 P 1 2, I mean sorry, 1 minus P 1 2 chi A chi A1 not star chi B2 here 1. Sorry, this is a mistake I made. Let me write it. Basically, I will not write it. It's not confused you. Let us write just the final one. This is actually, if you remember, this is actually a form. Right? If you can't remember, no, look on one of your earlier days, probably last class or last class expression. Let me show you what is. the last part of the Hartree-Fock theory, atomic Hartree-Fock theory, you get this. That's basically the Fock operator. Look at your derivation, somewhere you have done that. This one. Yeah, this one. This in this one. Right? In spin orbital. This is the one. This is space orbital. I don't have other classes. Yeah. So somewhere you'll find that. So basically what I'm writing here, this term will become, this whole thing will become R operating on Fock operator. Now we know that in the canonical Hartree-Fock thing, F operating on an orbital will give me values of the orbital energy epsilon A and the function back. This is equal to orbital energy is constant R A, right? This is basically we are writing as chi R and chi A, right? What are chi I? Chi A is the occupied orbital, chi R is the virtual orbital, and these orbitals are orthogonal. So this is equal to 0. I get equal to 0. So this whole term that we are writing here, the overlap between Hartree-Fock and single excited determinant is 0, right? This is important theorem. This theorem is named as Brillouin's theorem. What it says? It says that the matrix element between Hartree-Fock determinant, matrix element of the Hamiltonian between Hartree-Fock determinant and the singly excited determinant equal to. I have just proved this theorem. So this is a theorem and this is the proof. You just put them and you see you get a Fock operator operating on a orbital occupied orbital chi A. Chi A if chi A will give you epsilon A chi A back and chi A chi R orthogonal, so you just get 0. Okay, this is a very important theorem called Brillouin's theorem. No, remember that this is applicable because chi A's are orthogonal to each other. So this is not applicable to the atomic orbital basis. This must be applicable to the molecular orbital basis. Right? With this, now if we look at the equation number 1, what we get? We get E correlation. This guy equal to 0. What we get here? We get E correlation, the 0 correlation equal to first term is 0. So I get sum over of A greater than B, R greater than S, C, A, B, R, S, psi Hartree-Fock is B, R, S, right? Let us expand this. Psi Hartree-Fock. H is sum over of I, H, I. This is sum over of I, sum over of J greater than I, right? 1 upon Rij, psi AB RS, right? You see, it gets again simplified. A less than CABRS. What it gets here? It gets psi Hartree-Fock sum over of IHI psi ABRS plus psi Hartree-Fock 1 upon Rij. This is sum of I, sum of J greater than I. Right? What is this? According to Stater rules, this is equal to 0 because it's a one electronic operator and connected with more than one body excitation. Right? This is two body excitation. This is no excitation. So this will be equal to 0. Here you see, we get this term. A greater than B, R greater than S. According to Slater rules, this will give me just one term, that is RS, right? Which is equal to A greater than B, R greater than S, which is equal to RSAB minus RS. That's all. So what we get as E correlation, when we construct the operator, we have one body excitation, two body excitation, three body excitation. But finally, what we get? We get electron correlation energy, and this is exact. There is no approximation here. We have not talked about any approximation. What we get here is E correlation energy depends on only two electron integers, nothing else. Right? It depends on only two body excitation, two body excited determinants. It does not depend on anything else. It is not really true. It will depend, at least directly, it depends on only two body excitations, not one body excitation, not three body excitations. There's a reason for it. Reason is, you remember that in Hartree-Fock theory, what was missing? The missing was the Coulomb correlation. Whenever two electrons come close together, they must be repelled, they must be correlated. That's why when you have the electron correlation energy depends mostly predominantly over the two body. Right? There's no one body term here, at least in the wave function. The one body term will come here. We still did not know how to obtain this. So we have two part here, right? Now, if this is a element of the matrix, I can also have this element of the matrix, right? So you can write this in the matrix fashion. Let us not write it in it completely. So all we get as electron correlation as E0Ci is just this. In the molecular orbital integral, I have CAV RS RS antisymmetry. That's all. That is the electron position. Right? It depends on two electron integrals that can be, you can write this in terms of atomic orbitals also by expanding each chi in terms of pi's, right? So once you get the Hartree-Fock theory, you get the atomic orbital. From the atomic orbital, you get the molecular orbital, and from the molecular orbital, you construct these electron integrals multiplied with the coefficient terms CAVRS terms and add them all, you get the electron correlation. And this is exact, there's no approximation involved here, right? So you can understand that power of two body excitations. The electron correlation directly depends on two body excited determinants. It does not depend on one body excited determinant. That becomes zero because of Brillant's theorem. It does not depend on three body excited, three electron excited, the triply excited determinant or quadruple excited determinant, because anyway our Hamiltonian has at most two body terms, right? But the question is, how do we get this? Unless we know this, we don't have CL, right? This is again easy. All we have to done, first I have project with Hartree-Fock determinant. Now if I project with this, what I get? Left side I have this psi 0 AR CAR psi of AR A greater than B, R greater than S, CABRS. What I am doing here, my original equation, here I have projected with the Hartree-Fock. Now instead of putting Hartree-Fock, I'll put just one of the excited determinant. Again, because of intermediate normalization, I just want to put only one, not all. So I get here psi BS H psi A R, no, V S. I'm sorry, what did I do? Just lost my train. Right? This will become right side E naught. You have this one Vs, and then you have here psi Hartree-Fock plus A R C A R psi Hartree A R, and so on. Let me write another term. B greater than B, R greater than S, C A V R S, psi B S. No, I'm not writing it. Psi A V R S, so on. Again, same inspection. This guy, the first one, will become 0 because of Reynolds theorem, right? So I get 0. This I get as psi of A R C A R psi of B S is psi A R. This I'll be getting as A greater than B, R greater than S, psi B S is psi A B R S. You see, beyond that, this part will be have three body. This part will be, so have to have another one. A greater than B greater than C, R greater than S greater than T, psi B S is psi A B C R S T. Beyond that, everything else becomes 0. The moment it go beyond that, right side I have 4 body, left side I have 1 body. A difference of 3 bodies. It becomes 0. Right? Right side I will have what I have here. You see, this will become 0 because of orthogonalization. So I get E0 and I get this guy psi of BS psi of AR. Right? Now what we get here? I have a C A V R A. This is C A B C R S T. This will give me sum over of A R C A R psi B S H psi A R. You see, this term will survive only when B and there are two same, right? This and this must be same. Otherwise, you have a difference of more than 2. If this and these are entirely different, I can write it instead of ABC, let's say it is C, D, R, T, U. This will survive when B equal to C and S equal to T. Otherwise, they become 0. So I get only few terms here that will be incorporated here. Right side, you see, only terms will survive. This was some over of R, C here. Only term will survive when A equal to B, R equal to S. That means the two determinant must be same. So I get E0, T of, that's all. So from here, you can expand this using Slater rules, right? here we get this equation. Now the point I'm bringing it here is that for correlation energy, all we need only CAVRS. This is the guy we need, right? But to calculate this, I also need, you see, to calculate this, I also need this one, right? I also need the contribution for the single excitations. Now, if you project with two-body excitation determinant, you also get a term that has three-body and four-body. If you excite with three-body determinant, you also get a term which has five-body and six-body, not more than that. I mean, four-body and five-body, not more than that. Right? So for each, the result of CI, the resulting expression for CI energy may not be dependent on two-body excited determinant or three-body excited determinant directly, but they're indirectly determinant uh, because to compute this coefficient, we need all the different type of excitation determinants. Right? So that's all the CI is. Whole thing can be written in much more crispier manner, right? All you need to do, write them in terms of matrix. Okay? Let us do in the next class. We need to have the expression for the first one. This is, let's say, this equation we write as 2. This equation is write as 3. And then all other manners. So we have again project with psi A B, I mean C D E U prime, just to differentiate that. You get another equation, right? If you project by psi C D E U M N U M C D E, three body one, you get another set of equation, right? So every time you are projecting one determinant by one determinant, you are getting a set of equations, right? If you notice that, what are these? These are all are linear. Everywhere I have, these are the unknown coefficient. That's all we need to determine. We need to determine CAVRS. For that, we need CAR. For that, we need CRST. So we have a set of equations, set of linear equations, right? We will have something like this: C of AR psi ABS is psi AR plus CABRS psi BS this must be different. I'll write as B of B2 T is IABRS, and some other term will give me E0 of CAR. When you put the next equation, you can understand we get another equation which will give me E0 C of AB. The first one has given me this digest. This one equal equation into 1. Now you see get another equation here. Now if you inspect this equation, you can understand that these are the set of linear equations, right? With the unknown coefficient. And all set of linear equations can be framed in terms of matrix. right? It's just like ax plus by equal to c1, and that's like this equation. If you have 2 by 2, I have something like a1 x plus b1 y equal to c1. I have a2 x plus b2 y equal to c2. This will have this sort of equations. And how to solve them? You can solve them by constructing a matrix of a1, a2, b1, b2, right? Y equal to c1, c2. That's the equation you have to solve. So CI equation would be written in terms of this matrix. And how to solve this? We have to just diagonalize this one. That should give you the solution. Okay, that's all about CI. So this is full CI. The energy depends only on two body excitations, but the coefficient that depends on two body, one body, and all different. I'll stop here. We'll have spent some more time on these equations and the solution for this equation. The approximation that we have to make CI feasible and computable, and then we'll move for the production. Any question? Diksha, any question for me?
No, sir.
Okay, fine. Read about this part from Jabo 4th chapter.
Okay, okay, sir.
Okay then. See you.